So let's continue on from where we left off. We're going to see one more application today of the APS theorem, and then we'll end our discussion on that that particular topic and move on to considering the general operator situation and boundary conditions. So today I want to talk about the signature theorem. Okay, so let's begin with M and Mg being an oriented Riemannian manifold with boundary and yeah, for our purposes, maybe it's just better that we assume this. No, we don't need to assume it straight away. So with boundary of dimension, so of even dimension, right? So 2m. So n equals 2m. Later on, we'll actually move on to dimension of that is divisible by 4. Okay. So the definition. So actually, yeah, maybe we won't make this assumption right now. Let's just keep it. Let's just keep it of any dimension for the moment. Okay. So for alpha, beta, alpha. Let's see. Aha. So for alpha and beta K-forms on M, with, say, alpha equals to alpha 1 wedge up to alpha K, and beta equals to beta 1 wedge up to beta K, define an inner product on these forms alpha beta by just taking now the determinant of this. So these are just covectors, alpha I, beta j, I j equals 1 to k. Okay, and then extend to the whole of via linearity. Yes? Yes. You cannot write a general form in this way, of course, right? So this is a special form. Well, I mean, it's a K form that can be expressed as the wedge product of K vectors or covectors. And the point is that you initially define it for those, and then of course you can extend it to all of lambda m, right? Because a general form on lambda m is going to have is going to be a linear combination of these objects. Okay, so now with this, let's define, I mean, this should just be really recalling things. So this is Hodge star. So, okay, so so we have an oriented manifold, right? We've assumed that it's oriented. So actually the volume form, the volume element is really a differential form now, okay, because of orientability. So it's not just a density, it's a form, right? So letting mu g be the volume form, which is due to orientability, define a product star that takes us from k forms on M to n minus k forms on M by alpha wedge star beta is equal to g star alpha beta mu g. Okay, so that's the Hodge star. That's the Hodge star operator. Okay, so of course Hodge star acts on all forms and it maps back into the forms, right? So it's an operator on differentiable forms on the exterior algebra. Okay. So now the point is that the Hodge star operator is an isometry. Well, maybe I shouldn't say that. Maybe I should just say that this is going to map. So in the definition, let's just leave it that it maps forms to forms in this way. And then I'll say the Hodge star operator maps in the following way. It maps k forms to n minus k forms. And it's an isometry that satisfies star restricted to k forms is equal to minus 1 k n minus k, the identity on the k forms. Okay. So why do I want to think about the Hodge star? Well, the Hodge star allows us to describe the adjoint of the exterior derivative with respect to the metric through a composition of the Hodge star and the exterior derivative. Okay, so of course we can see that the Hodge star depends on the metric, right? And that dependency is exactly encoded in the definition here. So the adjoint also depends on the metric, and this now has a nice way in which we can express the adjoint of the exterior derivative. So the operator d star of g can be written as d star g restricted to k forms is equal to minus 1 to the n k minus 1 plus 1 Hodge star d Hodge star, right? And we can also write this now as minus 1 to the k of the inverse of the Hodge star composed with d. Okay, so these calculations, these lemata are readily verified. Oops. Through a computation. Okay. Now let's consider the situation that we have now with the Hodge star operator, we can define a certain involution on differential forms when we have a manifold of even dimension, right? So notation, recall that a map T on a Banach space, say, a bounded, so it has to be a bounded map, is an involution if T inverse is equal to T. Okay, so that's what an involution is. So with this, let's define, suppose, let the dimension of M equals N equals 2M, right? So it's even dimensional. Then define, so this character I'm writing is upsilon. So define this involution by the following. By upsilon of phi is equal to I k minus 1 plus m. So here the dimension is 2m, right? So this is half the dimension here. Hodge star phi. Whenever, so for phi in k forms. Okay. So maybe I'll give this as an exercise. Show that gamma mapping this space into itself has spectrum plus minus 1. Okay, so an involution has only plus minus 1 as a spectrum. So as a consequence, so we have now that the differential form split via the spectrum of this involution, right? As a consequence, we obtain that we define, or I should say define. So as a consequence, gamma splits this bundle, well, it's a bundle to via its spectrum, and so define plus minus of m to precisely be the eigenspaces plus minus of this operator upsilon, so that define this, and then we have that the full differential form split into plus of m plus minus of m. Okay, so what have we gained? So what have we gained? So the gain here is that gamma composed with the Hodge-Dirac operator d plus d star g anticommutes with the Hodge star. Okay, so the proof of this, well, let's leave it as an exercise. But you use previous lemma for expressing, so this is why I wrote it before, d star g in terms of d and the Hodge star. Okay, so once we express d in this way, this is just a calculation. Okay, sorry, all right. So as a corollary to this, we obtain that dH restricted to C infinity m of these positive forms actually maps us from the positive forms to these negative forms. So this you can see is very close in flavor to what we did last time with respect to the spin Dirac operator, right? With the spin Dirac operator, this also happens naturally in even dimensions. Okay. So this allows us to make the following definition. So on Mg Riemannian of dimension n equals 2m, so even dimension, we let, I really hope we haven't used the symbol S before for something, S equal to dH restricted to C infinity of these forms to be the signature operator. Okay, so this is what's called the signature operator. All right, so what can we say about this operator? So, so the first thing we can say is that S, I mean, it's easy to read off that it's of course a differential operator of order 1, but it's also elliptic. Okay, so we have that it's an elliptic operator. Good. Okay. Now we have the crucial proposition that's going to allow us to think about what we want to talk about next. So now we let the dimension actually be divisible by 4. Okay, so let Mg be a Riemannian manifold of dimension n equals 4k. Okay, then the following hold. Sorry, I need to also assume, sorry, okay. Suppose that G, so again we have this assumption that G is a product near the boundary. Then the following hold. Okay, so the first thing. So first of all, this bundle that I've defined, so this can be identified with the differential forms on the boundary. Okay, so we saw this also with the spin Dirac operator, that once we have this splitting, of course when we have the splitting, it's going to split into equal dimensions, right? So I should have really said maybe here, that was actually my fault. This not only, so in the exercise, the spectrum splits in this way, and the eigenspaces of -1 is isomorphic to the eigenspaces of 1. So that also fixes the dimension, right? So it has to cut up the bundle in a way that each of the, well, we'll get onto that in a second, but it splits it up into two sub-bundles which are of the same dimension. So, okay, the second point is that we can write S equal to sigma dt plus B now. So we're calling it B here. Okay, maybe. It doesn't matter. We can continue to call it B. What do I want to call it A? Let's see. Well, we'll call it B because it's associated with the signature operator. Well, actually, let's not do that. Let's well, let's call it A. Okay, where A is computed to be -1 to the K. So this is where the even. So this is the dimension divided by 4 plus P plus 1. Now I'm going to have EP, which I'll explain in a second. Now the now we have the Hodge star operator on the boundary, the exterior derivative on the boundary, and then again minus the exterior derivative on the boundary, such so where star dm is the Hodge star on the boundary, dm is the exterior derivative on the boundary, and okay, so I should really say that this is A restricted to P form on the boundary. Okay, so the point is that we can identify this positive bundle with what happens on the boundary, and then I can of course write this operator in this following way. So okay, so it has to be, right? It's always taking this form. So it cannot be anything but an adapted boundary operator. There is no the adapted boundary operator. I mean, there's lots of adapted boundary operators, but when we write it in this form, if you do a principal symbol, if you calculate the principal symbol of the A now from the expression that we have, it's clear that this has to be an adapted boundary operator for S. So it's for really the signature operator, right? Okay, so so let me just see very quickly. So let me just see. I just want to get this right because okay. Yes, it should be that we can sorry. So sorry. This is not true. This is M restricted to the boundary. That's what I thought. It felt a bit odd, right? So the reason that we can now consider A acting on the differential. So A is an operator that now acts on differential forms on the boundary, right? And that's really because, I mean, ordinarily A would be acting on the bundle wedge plus M restricted to the boundary, but because it can be identified, we now have the operator A acting on the differential forms on the boundary. Okay, and so E of P, or epsilon of P now, is equal to 1 for 2P form, and E of P is equal to -1 for a 2P minus 1 form. Okay, it's a little bit of stuff there just to state it, but anyway. So and the operator, so the operator A commutes with the following. Commutes with phi mapping to -1 to the power of p Hodge star of phi on p forms, preserving parity, so B now splits as follows. It splits in, A now splits into an operator on even forms and odd forms in this diagonal way, right? So this is now partial M even forms, partial M plus odd forms partial M. So of course, so this maps into itself. So of course, I mean, this whole thing is equal to the full exterior algebra on the boundary. Okay. So now, all right. So let me just give a proof sketch. So, so the expression for A simply comes from the definition of S. After a calculation. Again, the point is that we can use the expression that we have for the exterior derivative, or the adjoint of the exterior derivative, in terms of D and the Hodge star, right? And then we also now consider this restriction through this eigenspace of the to an eigenspace of the involution, and all of that information gives us this expression for okay, that gives us the expression that we want. Okay, so also note that the expression for A requires the dimension of M to be 4k, because it has a factor here of k. This is what allows us to assert the preservation of parity and the commutativity of phi mapping to -1 to the p star phi. And that gives rise to the decomposition, right? So it's not so important. What's really important is really the corollary of this. Okay, so the corollary is that AV is obtained by conjugating a odd, and therefore the eta invariant of A is equal to just double of the eta invariant of A EV, or equivalently the double of the eta invariant of A odd. So this is a lowercase s, it's not the s of the of the operator. So why is this true? So if it's a conjugation, recall that since AEV is equal to some T inverse A odd T, we have that the spectrum of AEV is equal to the spectrum of A odd. And of course we have, and this is up to multiplicity, counting multiplicity. So as a consequence, of course, we need to know that there's discrete spectrum for this, right? So we know that there's only eigenvalues. So therefore, we have the statement as required, right? Okay, now that we have that information and we have a description of the eta invariant of the signature operator in terms of this odd and even parts, let's now consider an important polynomial. So this is the Hertz-Bruch L polynomial. I mean, after all, we want to calculate something from the index theorem. So let L of x be equal to square root of x divided by hyperbolic tan of the square root of x, expanded as a formal power series. Then L of omega. So we have so this is for the curvature 2 form now in this context. For omega curvature 2 form, we write this to be equal to P of L of omega, which, let us recall what that is. So this is the exp of this map lambda acting on log L, acting on log P of omega, where P is now the Pointry eigenclass, right? So so this is now going to be in C infinity M 4 star M. Okay? Okay, so finally with this we can describe the so-called local index theorem. So on a Riemannian manifold, on an oriented of dimension m equals to 4k with G product near the boundary, the index of the signature operator with now the APS boundary conditions, right? So the APS boundary conditions, of course, are given in terms of this operator S. So I should have also said that this operator, sorry, not the operator S, the operator A. And the operator A is self-adjoint, right? So so maybe where A is self-adjoint, okay. So maybe I'll put that up there. So so this APS is precisely now the boundary condition for S B APS in terms of the operator A, and this index is equal to the integral over M of L omega. So again, we're picking out the highest order form, and because the dimension of M is 4k, we will have a value, right? Because this exponential map of this construction involving the Pontryagin forms lands us in the exterior algebra of multiples of 4. Okay, and this is minus the dimension of the kernel of A even plus eta of A even at 0. Okay, so the point is that before we had the eta invariant and we had a half in front of it. Of course, we would still get a half now if we use A, but we're now using the A even, and so as we saw before, this is going, so the eta invariant of A is twice that of the eta invariant of the AEV, right? And the same goes for the kernel. Okay, so this is a very important index theorem, but and it generalizes an index theorem due to Hertzsprung in the context of closed manifolds. But what's more important from this is its corollary, which is also in the closed case was due to Hertzsprung. So this is the so-called signature theorem. And the signature theorem says this. The quantity index SAPS plus the dimension of the kernel of AEV is equal to the signature of M, where sign M is the signature of a non-degenerate quadratic form in the homology H2K of M, the cohomology, sorry, and therefore, what do we have? We have the signature of M, is equal to the integral of L omega of M minus eta B A EV at 0. Okay, so this is really a remarkable theorem, right? So I should just say that the sign of M, so I mean we can describe it in terms of this index plus the dimension of this kernel, but it's really an object that's topological, right? So it just really lives. It's a non-degenerate quadratic form. I don't want to get into the nuts and bolts of it because it involves a certain thing called the cup product in the relative homology groups, and I don't want to really get into it. But the point is that it's a signature of a non-degenerate quadratic form. So a priori, it doesn't involve any operators or boundary conditions or anything like that, right? So it's really living at the level of the topology. So the happy circumstance is that in this situation, it can be described by the index of an operator corrected by adding the dimension of a kernel of something that also, in some sense, comes out of the operator. So in fact, the signature is a topological invariant, right? So remark. So this is a truly remarkable formula. No pun intended with remark and remarkable. So the signature of M, so this is a topological invariant. The object L of omega now, this is differential geometric object, right? It's an integration of something constructed out of the curvature of the of omega. Lastly, A even at 0 So this is actually a spectral invariant. So the point is that if we scale the metric, for instance, right? So what does it mean for it to be a spectral invariant, right? So, i.e., if we scale G, eta A of S, A even of S, changes, but eta A eve of 0 remains fixed. Okay, because the kernel doesn't move. Of course, if you scale the metric, the eigenvalues the non-zero eigenvalues can move and get stretched out or contracted depending on how you modify the metric or scale it, which is, I guess, the simplest modification. But the zero eigenvalue remains fixed. So, so this is really a spectral invariant. So there are really three invariants or three interesting objects that appear in this formula. So, in some sense, this is quite remarkable, and this is capturing that level of interest that one has in the APS theorem, the AS theorem, the Atiyah-Singer theorem, in the context of a closed manifold. So when we don't have boundary, because when we don't have boundary, we have that the analytic index equals a topological index, right? But we saw that last time that when we go to the APS theorem, we no longer can talk about the integral against the A hat form as a pairing of a cohomology class, because that's no longer well defined. So that's still a geometric object. So we don't have this nice relationship between sort of topology and something analytical. Whereas here we really have a topological object on the left hand side, and so in some sense this is capturing the spirit of a true sort of topological formula. Okay, so this is all I really have to say in terms of applications. Maybe we've even spent more time than necessary on it, but I just wanted to sort of at least list the applications that really motivated Atiyah, Patodi, and Singer in terms of their seminal work on this topic. One can go further and examine using the signature theorem to try and extract out something like an Euler form, and then a generalization of things like the Gauss-Born formula from the APS theorem, and so on and so forth. So there's an entire smorgasbord of interesting results that really follow from the Atiyah, Patodi, Singer index theorem. But for the purposes of this course, let me just leave it here. So before we move on to a new topic, maybe I'll just see if anyone has any questions regarding all of this. The signature encodes, so one has to look at the relative cohomology of the interior to the boundary. And then there is a certain way of embedding that into the H2M. And then there is a certain product called the cup product, which gives a quadratic form in the homology class. And it's this quadratic form. It's a non-degenerate quadratic form. So this is going to have a signature of some sort, right? And that's what the signature theorem. That's what the signature of M actually is. So it really just measures somehow the topological information of the interior to the boundary in some sense. But it's, nowhere in that does there appear something like an APS boundary condition or anything operator theoretic, right? So the remarkable thing is that the signature can actually be written as the index of this operator plus the dimension of this kernel, and then that's really a topological object, right? So we can move these. So if we move the metric, of course, the operator also moves. Of course, the kernel of AEV does not move. Potentially, well, actually, it could move. The kernel, if we move the metric, it could move. That's true. But the sum of the two remains invariant, and it's equal to something topological. Okay, let's now close the chapter on that and begin a new chapter. So, elliptically regular boundary conditions. So, arguably what we're going to consider now is one of the most significant sort of updates on the theory of boundary value problems. And really, I should say that what we're going to talk about today was initiated by Christian Baer and Werner Ballmann in their paper on where they considered boundary value problems just in the case where you have a adapted operator on the boundary that's self-adjoint. And they were able to prove that a very large class of boundary conditions, arguably the most important class of boundary conditions in the context of global analysis, can be given a very interesting description through. So one can somehow cut up the check space with respect to the boundary condition, right? And that allows very simple proofs of very deep results, as we will see. So elliptically regular boundary conditions. Okay, so there's a new chapter. So now let us return to the situation where we had before. So mu is a measured manifold with compact boundary. We had E, so this is already listed somewhere. This is already listed somewhere in the notes. These are Hermitian bundles. And we have D that takes us from E to F. And it's elliptic. And the last thing that we have that we want is that D and its formal adjoint are complete. Right, so so compactly supported sections in the maximal domain are dense. Okay, so now let's recall. Let's go back to what we did before. So we have that B contained in H check of D, right? So remember the check space. In this situation, we can always pick, so what is the check space, right? So remember that in this situation, there always exists an omega, a bisectorial and invertible adapted operator to the boundary. And so we can always write the check space as this, as the check space of that operator. With respect to that operator, and the point is that it doesn't matter which operator we choose, right? We've already seen that before. So we say B is a boundary which is a boundary condition, i.e. closed subspace, elliptically regular, so we may have even defined this before, but let's just recall it. If, so this is a very qualitative definition, right? It's a very simple definition to remember. So we have that the boundary condition and the boundary condition corresponding to the adjoint, right? So I'll write that. So this is H half contained in M F, where what B perp or B dagger, sorry, is equal to the restriction of V to the boundary such that V is in the domain of DB adjoint, right? So this is what we defined as this boundary condition. So what it means to be elliptically regular is that both B and the adjoint boundary condition are both sitting in H half. So remember that this check space contains one piece in H half and one piece in H minus a half. And it does so non-trivially. And what this is now saying is that both B and its adjoint are sitting in H half. So the goal of this section is to obtain a powerful characterization of such boundary conditions. Okay, so it's a very powerful tool. So we've already seen, okay, so in the context of the language of the Atiyah-Patodi-Singer index theorem and all the reviewing we've done, we talked about Dirac type operators, all of which have self-adjoint adapted boundary operators. We've seen in explicit circumstances that we also have this nice form when we have product near the boundary, or we have a Dirac bundle for which the connection and metric are constant in this in a neighborhood of the boundary. We've seen that there are lots of such elliptic boundary conditions, right? So explicitly, we have already seen. Let me just say we have already seen that such boundary conditions are plentiful. Okay, so what's really at the heart of the plentiful, the reason that they're plentiful? So the point is that we show that given any adapted operator on the boundary, we can extract out an operator, we can extract out an APS boundary condition for it. And the point with the APS boundary condition is it's defined in terms of an adapted operator to the boundary that we extract from this operator, which is invertible omega sectorial. And that allows us to somehow decompose the check space. So the underlying philosophy here is that we have a boundary condition and we use the boundary condition to decompose the check space that allows us to compute things in a nice way, right? So that's really sort of at the heart of all of this. So explicitly, given any inward pointing vector field T on M, on partial M, and any adapted boundary operator A with, well, satisfying the principal condition that we want now with respect to, sorry, this is A, with respect to this vector field T, so this is dt inverse composed with dx psi, right? The boundary condition B APS of A, which is what? This is exactly equal to chi of A little a h half partial ME, where we recall that the little a is half of the minimum of the real part of the first, well, okay. Yeah, so, well, I should say, what's the best way to write it? Negative minus 1 and negative plus 1, negative 1, where this J is in the real part of the spectrum of A, right? So this is how we defined the APS boundary condition. So the point of this is, okay, so the point here is, so underlying this, is elliptically regular. So we've already seen this in the APS section. Okay, so when we were talking about the APS boundary conditions, this is how we define the APS boundary condition for a general adapted operator A on the boundary. Okay, so what is behind this? Behind this, as we saw in the previous lemma, as we saw in the proof of this fact, is that we can decompose, we can write h check of D as equal to h check with respect to this little a of D, okay, of D naught actually, right? So this is the model problem now that's induced by this adapted operator A subscript A. And then the computation is very easy to show that this is elliptically regular. All right. So we want to move beyond just talking about, so the point is that we've talked about adapted operators on the boundary, but we want to move beyond that. To be totally flexible, we should really be talking about general projectors that allow us to describe the check space, right? So to proceed, we consider the a class of projectors. Okay, so let's make a definition. So this is a boundary decomposing projector. I would like, so we say, so if maybe it's a good idea, maybe I should just say at this point, it's a good idea to have the P plus described by something like B proj or something in the LaTeX, because I want this to be a calligraphy P. So we say P plus is a boundary decomposing is boundary decomposing for D if these 3 points hold. So P, maybe I'll write it as that, P plus maps H alpha on the boundary is a projector for alpha in the range -1/2 to +1/2. Okay? Number 2, P plus takes us from the check space of D. It is a projector on the check space. And we want the P minus to be defined as 1 minus P plus, and that's going to take us from, so the range of this is going to be in H1/2 of here. Okay, so the third condition, I don't actually even have to write this down because I've said that it's a projector, but just for completeness, let me just write that the H check of D norm now can be written as P minus of U in H1/2 of M plus P plus of U H minus 1/2 of M. Okay, so the reason I don't have to write number 3 is because H1/2 is already a subspace of H check. So now if I have a projector, I know that the range is closed. So its range is closed and it's landing me in H1/2, then it means that the H check norm must be comparable to a H1/2 norm. Okay? All right. Okay. So we've seen plenty of these, right? So this is just generalizing what we've already seen, but let's just list them. So the first example I want to list, and this is sort of really the historical, well, okay, second example is the historical one, but the first example we've already seen. We take chi plus of A for A invertible bisectorial adapted boundary operator for D. Okay, so that was what we were really concerned with before we moved on to the APS theorem, right? So there we talked about the general problem, and what came out of the wash in the general problem was that I can choose any invertible bisectorial adapted boundary operator, and I can understand the check space in terms of that. So in this language now, the chi plus of A is a boundary decomposing projector. The second example I want to give is what we saw very early on in the topic. So when M is compact, we have P of C, a Calderon projector. So P of C takes us from H minus 1/2 to H minus 1/2 ME to, oops, all right, let me just, to H minus 1/2 ME. Calderon projector, i.e. we have a Calderon projector, but there could be many, i.e. the range of, so P of C, so C equals to P of C of H minus 1/2 is precisely the restriction of elements in the kernel of the maximal operator, right? So we've already seen that. So P plus PC is another choice, is boundary decomposing. Okay, so I mean, just I'm giving these examples to sort of, you know, say that the class of objects that we're looking at is non-trivial, but we want to have as much flexibility as we can, because I mean, choosing a projector fixing a boundary decomposing projector, in particular by condition 3, which allows us to really write the norm of H-check. Well, it gives us an alternative norm for H-check, right? So that's really saying that we are understanding. So, I mean, the norm here, it's also induces an inner product, which is not so important, but it's really changing. It's really giving us a geometry for the check space via the boundary decomposing projector, right? So that's really the fundamental thing to keep in mind. And having that flexibility just means we can do more. We might want to choose a boundary decomposing projector depending on the problem, and then understand boundary conditions with respect to that boundary decomposing projector, right? So that's really the point of view here. Okay, so motivated by our analysis of H check A of some D naught and its accompanying space H hat A of D, we define the following. Okay, so define H hat of D now to be equal to P plus star of U in, well, what am I doing? This is a norm I'm writing. Okay, so this is equal to H hat P plus D adjoint with norm, well, sorry. Let me write this explicitly. So this is P plus H a half partial ME, sorry, P plus star, plus P minus star H minus a half partial ME with the norm now being equal to this, right? So P plus star of U H a half partial ME squared plus P minus star U H minus a half partial ME. Okay, so this is sort of what I'm talking about when I say that there's a geometry, because when we compute the dual spaces now, I mean, the dual space is really the hat space, and that sees the projector, right? It sees the way that we've cut up the space in terms of the projector. All right. So just to fix our notation, I think we've already mentioned this before anyway, but let's just fix our notation. So if we have B, a Banach space B, so writing this sum means that we have bounded projectors that realize this. We define the B1 star to be equal to the projector of B1, B2 star adjoint acting on B star. And similarly, B2 star is the projector B2 killing B1 acting on B star, right? The adjoint space. Okay? So if it's a Hilbert space now, that B star and B are the same. Okay, so with this, we're going to make a definition now. It's a long definition, but it's an important one. So this is the so-called graphical L2 decomposition. So let B contained in this H check space of D be a boundary condition. And P plus boundary decomposing. For D, okay, for D. Well, D is implicit. Suppose that, okay, so condition 1, there exists mutually complementary subspaces W plus minus and V plus minus of L2 of the boundary such that W plus minus O plus V plus minus are equal to P plus minus acting on L2. Okay. Secondly, W plus minus and the W plus minus star are contained in H half and are finite dimensional. Pardon me. Okay. Lastly, there exists a bounded linear map from G that takes us from V minus to V plus, such that, so first I want G of V minus intersect H half to land me in V plus intersect H half. And I want the adjoint of now V plus star. So the adjoint map will now take us from V plus star back to V minus star, right? So this intersect with H half, I want it to land me in V minus star intersect h a half. And the b now being equal to v plus gv, such that v is in v minus intersect h a half partial me plus w plus, which is what? Which is exactly equal to the graph of g restricted to h a half plus w plus. Okay, so so suppose that this holds, then we say that b is graphically L2 graphically decomposable with respect to p plus. Okay, so it's a bit of a difficult definition, right? But what is it really saying? So it's really saying that I'm able to write. So what is the splitting, right? So I have L2, say. So I have my space L2. So let's denote L2 by these two subspaces. So this is P minus. Of course, it doesn't have to be orthogonal. So this is P minus L2, and this is P. So this is P plus L2 on the boundary. So it's saying that if this is possible, then I can write my bound. So it's saying that I can write up my so V minus is some subspace contained in here, right? So maybe I didn't write this. I didn't draw this all that well. Maybe the better way to draw it is really two-dimensional. So maybe let me try that. So I'll try and draw the. So this is the P minus, and then okay. So maybe I'll use a different color for this, just to highlight it. Well, maybe just change color and do it. So let me draw. So this is my P minus. So, oops, I lost that there anyway. So, so this is my P minus L2 of M, E. Okay, and now let me, I don't know, use blue, I guess, to draw. Oh, it's not a regular blue. That's probably not good either. And let me draw. So this is my P plus. So color, style, color. Okay. So now the point is that maybe I have some subspace here, right? So so these are not intersecting. So maybe I have some subspace. I'll draw it back in red. So I have some subspace here, which is my V minus, right? Of course, the way I've drawn it is not correct because the amount of error term has to be finite dimensional. So, well, okay, in this case, maybe it is because it's a finite dimensional space. So maybe let me further decompose this into. So green's probably not a good color for this. Maybe I'll just draw it in white. So let me further decompose this plane and call this V minus, and this is W minus, right? So similarly, I would have a decomposition, say, of of this plane here into into V plus and W plus. And what it's saying is that now I have a map that takes me from the V minus to the V plus, right? So this is the map G, and the amount of error term, so I can write my boundary condition now as a graph. So it'll be some subspace that's the sum of the two, right? It'll be a subspace that, this is really testing my drawing skills, but anyway, so it's a subspace that would go like this, say. So this is V plus GV, and the amount of error term I have is just this finite dimensional subspace W plus. Okay, so that's really what this is saying, right? That I can decompose my boundary condition in a really nice way into these parts, the way that we cut up the check space with respect to this boundary decomposing projector P. Okay, so we're running out of time, so let me just leave you with the theorem that we will get to in course. So what is the theorem? So the main theorem here, so maybe I should attribute it. So originally it was due to Baer-Ballman, and then this was extended, so that was for adapted operators with which are self-adjoint, and then Baer and myself, we extended this to the general first-order elliptic operators, but still for spectral projectors, right? So this was all in the context of spectral projectors, and then it was in the recent work with Magnus Goffeng and Herman Sarachandran that we extended this to this general class of boundary decomposing projectors. So you're really getting this from the hot out of the oven, because it's not even published yet. Okay, so all right. So so maybe when I write this out in the lecture notes, in the theorems, I will really give all of the necessary stuff, the hypothesis, but for our purposes, let's just write it here. So given P plus boundary decomposing projector, boundary condition B subspace in H check of D is elliptically regular if and only if B is L2 graphically decomposable with respect to P plus. In this case, so B, okay, so the annihilator of this boundary condition, so this is really so remember, this is the sigma naught star of the adjoint boundary condition. This is going to be given as the annihilator in the landing us in the check space, the hat space we've just defined. So this is actually equal to U minus G star of U, such that U is in V plus star intersect H half partial N. Okay, so so next time we'll look at this in particular, and actually I'm going to delay the proof of this maybe to a few lectures on, because I think it's best to first discuss some of the consequences of this, and in particular show how powerful it is in the context of, for instance, index theory.